Okay, good morning, everyone. Welcome to the keynote session of today. So it is my pleasure to introduce our keynote speaker, Dr. Maryam Shanechi, a visionary and trailblazer at the intersection of neuroscience, artificial intelligence, and engineering. Dr. Shanechi is the Alexander A. Sovchuk Endowed Chair and Professor of Electrical and Computer Engineering, Computer Science, and Biomedical Engineering at the University of Southern California, where she also serves as the founding director of the Center for Neurotechnology. Dr. Shanechi's groundbreaking research is shaping the future of brain-computer interfaces and computational neuroscience. Her work integrates advanced AI with neural engineering and pioneering a new generation of BCIs that not only restores lost motor function, but also aim to improve mental health by decoding complex mental states such as mood. Dr. Shanechi's academic journey began with a bachelor's degree from the University of Toronto, followed by master's and PhD in electrical engineering and computer science from MIT. She has received numerous prestigious honors, including NIH Director's New Innovator Award, NSF Career Award, ONR Young Investigator Award, OneMind Rising Star Award, among many other recognitions. Please join me in welcoming Dr. Maryam Shanechi, whose keynote today will offer a fascinating look into the AI-driven neurotechnologies and how they push the boundaries of neuroscience in everyday life. Thank you.
Well, thanks so much for that kind introduction. It's a pleasure to be here today and talk about some of the work that we've been doing on developing AI-driven neurotechnologies. So as we all know, brain disorders are actually a leading cause of disability worldwide, affecting tens of millions of patients. And unfortunately, we are not very good at treating them. So if you think about something like major depression, 20 to 30% of patients are treatment resistant, whether drugs or psychotherapy. So the question is, what do we do for these patients? Now, based on the understanding that these disorders are signs of abnormal electrical activity patterns across large-scale brain networks, one idea could be to try to directly decode and regulate these abnormal activity patterns towards alternative and potentially transformative therapies. So what do these activity patterns that I'm talking about look like? I'm showing you electrodes that are implanted in the human brain. These are intracranial EEG electrodes or ECOG electrodes. And these are the signals that we record from them. So you can see that these signals are very complex spatiotemporal patterns. They're noisy, they're high dimensional. There's no clear pattern in the signal that would, for example, tell you what somebody's mood is at a moment in time. So we envision building closed-loop system that would model these complex activity patterns, decode from them an underlying state of the brain, let's say mood in depression, and then use that as feedback within a controller that would then adjust therapy parameters, such as deep brain stimulation, frequency and amplitude, such as drug dosage, or any other mode of therapy that you can envision, in order to then take the brain to a target healthy state. Now, this is an example of a closed-loop control system. And as engineers, we're actually very good at designing these systems. For example, think about autopilots. But unfortunately, we still cannot do this for the brain. And you may ask me, okay, why is that? And of course, unlike an engineered system, we did not design the brain. It's an immensely complex system of billions of neurons with unknown dynamics, and that introduces a huge AI challenge to build data-driven models of this complex system and to come up with data collection frameworks that allows us to do this kind of modeling. So that is exactly what my lab focuses on. So we work at the interface of AI, neuroscience, and control theory to build these brain-machine interfaces and neurotechnologies that can restore movement, let's say in paralyzed patient, but that can also go beyond that and think about restoring emotional function in neuropsychiatric and mental disorders. All right, so in particular, there's two types of brain-computer interfaces that we can think about building. The first type are for motor function. You heard a lot of beautiful talks yesterday, both from academia and industry about these BCIs. So in these BCIs, essentially what we do is we record the electrical activity patterns from the brain. We use those to decode an intended movement, then use that intended movement to control the prosthetic and provide visual feedback to the subject. So if you think about these BCIs, essentially the controller here is the brain itself. It's trying to control an external device. So we also work on building these kinds of BCIs. But when I started my lab, we thought about these second type of BCIs that I mentioned that kind of try to do the opposite. So instead of the subject trying to control the prosthetic, now the goal is to decode a mental state from brain activity and then regulate the brain activity itself. So what I'm going to do today is to first show you how we think about the second type of BCIs for regulation of abnormal brain states, and then talk about some general AI challenges that we've been trying to address that can be beneficial for both of these BCI types. All right. So regardless of what kind of BCI we want to build, the first challenge, of course, is to build a decoding algorithm that would decode that brain state. Now, doing this actually is quite challenging for mental states such as mood. So when we started working on this problem, actually decoding of mood had not been demonstrated before. So to solve it, we first started by collecting the right data sets in collaboration with Chen, who's a neurosurgeon at UCSF. We recorded neural signals from a large-scale network of brain regions in epilepsy patients over a week to 2 weeks from hundreds of channels. And then while these patients were in the hospital, we asked them to intermittently report their mood using an iPad-based questionnaire, which essentially asked them, okay, how do you feel? And this we could do just a couple times a day. Obviously, you can imagine you can't ask somebody 10 times a day how they feel. So it gives you a couple labels of mood per day. So then this was the data set, and we had to train our decoder. Now, this is a very challenging machine learning problem to build these decoders because we have this very high-dimensional neural feature space to model, but very sparse mood data to model it with. So in order to solve this problem, we actually developed a dimensionality reduction methods for brain activity signals that essentially first said, okay, I have this very large network. I can't model it possibly. So let me first identify smaller subnetworks that are good enough for decoding. And then even within these smaller subnetworks, further reduce dimensionality by fitting this model that we call a dynamical system model or a linear state space model. And I want to talk about this model a little bit because I'm going to use it throughout my talk. So here, neural activity in red is represented in terms of a blue state, the X, which is lower dimensional. And then you also describe how the state of the system moves from one time to the next time. So you describe the temporal evolution in terms of a lower dimensional variable. So this is a latent state dynamical system model. So once we did this dimensionality reduction, then we only related that reduced dimensional state to our sparse mood labels. And doing this, we showed that we could indeed decode mood in every individual from their brain activity for the first time. So this was very exciting and opened the door to tracking of mental state. So this was great, but then the next question was, what are these subnetworks that are mood predictive? So what we found was that while we were doing these modeling in an individual by individual basis, across our patients, our decoder always picked consistent limbic regions for mood prediction. And more interesting than that, we found that in 60% of the individual, this part of the brain called orbitofrontal cortex was the most mood predictive. Now, this is interesting because in collaboration with N.E.W, we actually stimulated in orbitofrontal cortex. And once we did that, mood symptoms were actually alleviated. So patients went from describing their feelings to be on the sad side or a little bit nervous to describing it as being calm, cool, and collected and feeling a lot better. So these two different studies, one based on machine learning completely, one based on stimulation, arrived at this common node, orbitofrontal cortex, and indicated its significance in the emotion regulation system. Okay, so that's how we started decoding these mental states. And what you notice is that we use this linear state space model, right? And these models, these linear models, are actually quite widely used in BCIs. Think about Kalman filters. They're all based on this linear state space model backbone. And the reason these linear models are so popular, one reason for it, is their ability for flexible inference. Meaning the same model can allow you to do real-time or causal decoding, what we call filtering, non-causal decoding or smoothing, and inference or decoding even with missing neural samples that can happen in wireless BCIs quite often. But of course, a major challenge with these linear models is that they do not capture nonlinearity, and therefore they may not give you the best performance. Now, in parallel to this, there's been a lot of beautiful work done on developing deep learning models of neural activity patterns. But they focus mostly on offline analyses, and therefore they don't allow you to do flexible inference. So in a recent paper, our goal was to try to achieve the best of both worlds. Can we build deep learning models that capture nonlinearity and achieve flexible inference? And we did this by developing an architecture that we call DEFINE, for dynamical flexible inference of nonlinear embedding. So what's the idea? What's the intuition behind DEFINE? So the idea behind DEFINE is to try to capture the nonlinear representation within a nonlinear manifold embedding. Think about that, if it's too much technical jargon, as just the shape over which your neural state is moving. So like this donut or torus. This is a nonlinear shape because it's not a hyperplane. So if I capture the nonlinearity in that manifold or in that shape, then what I can do is to describe how my state moves on this nonlinear shape in terms of a linear dynamical system model. So on top of it, I describe things linearly, but the shape itself is nonlinear. And then I can learn the shape and the dynamics jointly end-to-end to predict future neural activity, for example. So this allows you to achieve flexible inference because of that linear backbone, yet achieves nonlinear modeling. So that's kind of the intuition. Now, for those who are technically inclined, just a little bit of a generative model. So here you have neural activity. As I mentioned, we assume there's a latent manifold layer that gives rise to it. We describe the relationship nonlinearly based on an MLP decoder network. And then on top of this, we describe the dynamics according to a linear dynamical system model, as I mentioned. So this allows us to achieve flexible inference once we learn it, because using the encoder, we can go on the manifold, then use a Kalman filter, because everything is linear there, that does causal, non-causal, flexible inference. And we can also achieve it at the presence of missing samples. But if you care about the methods, of course, there's in the paper more. Okay, how does this work? We tested this on, in this case, movement data set with monkeys reaching and grasping to diverse locations in 3D space while their neural activity was being recorded. And the goal was to decode their movement from their brain activity. So first, what we confirmed was that indeed DEFINE can do flexible inference. So this is real-time decoding of movements with more and more missing samples. And you can see that we can succeed in doing this. We also showed that with the same exact model, we can do smoothing to do better decoding, of course, because you lose future data as well. And if you notice, up to 40% of samples missing, we essentially are doing decoding without much degradation. So this shows the robustness that we wanted. Now, how does this compare with alternative models? So first, of course, let's look at linear models that I said are very popular. DEFINE does better, of course, by capturing nonlinearity across all regimes. Then we also compared with the benchmark sequential autoencoder, or LFATs, that at the time was kind of the state of the art, and Define also outperformed that. But this performance improvement was especially prominent when you had more and more missing samples. So if you look at how much performance we lose as we have more missing samples with Define versus LFAS, Define has much lower degradation, showing that robustness for wireless BCIs that we require. All right, great. So far, we've talked about these models for decoding of behavioral and mental states. And these models that I've shown you are unsupervised models in the sense that you first train this model just based on neural activity, and then you relate that model to behavior. Now, a major challenge, though, that arises when you're thinking about decoding a particular behavior or studying it is that the neural activity patterns that we record do not just relate to that behavior. So let's say right now I'm moving my arm, I'm talking to you, maybe I'm hungry, thirsty, nervous. All of those states simultaneously are represented in the brain. So can we disentangle those brain patterns that are just related to the behavior that we care about? That was the next question. So let's formulate and formalize this problem. Let's say I have some neural activity that I'm recording, some behavior I'm measuring, let's say movement. Now, if you think about the brain states that give rise to neural activity, it may be that just a minority of them are related also to behavior. Essentially, these green behaviorally relevant states could be a minority of all of the states. So if I learn a model just based on neural activity, unsupervised, what can happen is that I may actually learn those red states that, while of course exist in neural data, are not behaviorally relevant, and they may actually mask or confound the extraction of those green states. So with this motivation, back in 2020, we developed this learning algorithm called PSID, which is a joint model of neural and behavioral data. And its capability, the new capability it provides, is that it can fit this linear dynamical system model, but can disentangle the behaviorally relevant state and extract those first so that you extract them more accurately. And the algorithm is based on projection methods of behavior onto neural activity to find shared subspaces. Again, a bit technical. If you're interested, you can go to the paper. But how does this work? So we tested this again, my favorite data set. This is from Bijan Pesaran's lab, by the way. It's an awesome data set. So we tested it on this reach and grasp data set. We first compared PSID to the exact same model trained on supervised, which I call neural dynamic model. And you can see that regardless of the latent state dimension, PSID did the decoding more accurately. But more interesting than that, it could do this better decoding using a much lower dimensional state, in this case 5 times lower. And the same benefits held over nonlinear models. So the reason for this is, of course, this capability to tease apart and isolate just those states you care about so you can get them more accurately and more efficiently. And of course, for neurotechnologies, this is key, and as well as for scientific investigations. Since then, we have extended PSID in many directions. Just this past year, one of my students developed an extension that can give you shared dynamics between not only continuous signal modalities, but generalized linear, so Poisson, I don't know, categorical decision choices, so you can handle all of those modalities analytically. Another student of mine extended it for identifying shared interactions between brain regions or inter-area communication. So I'm not going to go into the details of these. You can look at these papers. But at the end of the day, PSID and its extensions were all based on this linear dynamical system backbone, which again is a powerful model, interpretable ability for flexible inference. But we know nonlinearity could also be important in some applications. So the next immediate step for us was to see if we can develop a joint neural behavioral data model that also captured nonlinear representations. And we did this in a paper that appeared just last year, which develops this deep learning algorithm called DPAD, or Dissociative and Prioritized Analysis of Dynamics. So what's the idea here? So the idea here is that we write this relationship between neural activity and behavior in terms of 4 interpretable mappings. The mapping from the neural activity to the latent state that I've been talking about all along in my talk. Then the dynamics or the evolution of these states, and the mapping back to neural activity and to behavior. Now, if you think about a linear model, all of these mappings exist. They're just linear. So how do we make this nonlinear? We allow the mapping, each mapping to be a nonlinear transform as you wish, using a neural network model for it. So this allows us to go nonlinear. It allows us, with the proper changes of the loss function, to capture behaviors that are categorical, capture behaviors that are intermittently observed, like mood reports, and it doesn't require really trial structure. So you can actually use naturalistic, real-world, everyday neuroscience data for fitting DPAD as well. So again, I'm not going to go into the details, but just give you an intuition of how DPAD does all of this. So essentially, it's a 2-section recurrent neural network model, or RNN, that you jointly train with neural and behavioral data. In the first section, what you do is you ask the network to predict future behavior from past neural activity. By doing that, we show that the network essentially learns those behaviorally relevant green states that I talked about. Once we learn those in 2 optimization steps, then we ask the network, OK, how much of neural activity is not already explained with these behaviorally relevant states? And please predict the rest. And by predicting the rest in the last 2 optimizations, the network gets the other residual neural states and dynamics. So that's kind of the intuition, and the details, again, you can refer to the paper. OK, so for DPAD, we wanted to look at multiple data sets and look at generality across different modalities of neural activity. So in addition to our reach and grasp data set, we also looked at a saccadic eye movement data set from Bijan's lab, in which monkeys were saccading to different direction while we were recording from prefrontal cortex. We looked at 2 public data sets from the Savis and Miller labs with cursor movements and premotor and motor-cortical activity. And we looked at 3 neural modalities: spiking activity, raw LFP activity, and LFP power band activity. So the first question here, of course, was, can it actually extract the behaviorally relevant states better by having nonlinearity in it? So we looked at this question by comparing it essentially with PSID, that we know is the linear counterpart, does very well in decoding behavior. And we found that across all of these 3 neural modalities, the nonlinearity actually did help us in decoding behavior, meaning these movements or eye positions, showing that there is nonlinear representation. But more interesting than that is the fact that by putting these side by side, you can actually look at the degree of nonlinearity across these modalities and compare them. And what you'll notice is that the raw LFP modality benefits the most from nonlinearity. So much so that using the raw LFPs, we could decode movements better than using the traditional LFP power band features that we usually use in BCIs and neuroscience to study neurodynamics or decode movements. So what this implies is that there are behaviorally relevant features and dynamics in LFP that are lost if you just compute powers. There's more stuff in there that you can extract with these nonlinear models. And in some cases, doing this could even decode movement better than spikes, which is very interesting. Not in every data set, but in some data sets showing the potential for these field potentials as a modality for BCIs. Now, that was the behaviorally relevant states and decoding of behavior at the end of the day. This is a neural behavioral model. So the next question was, can it also predict neural activity well? So what we found was that indeed it could. So not only did it have better behavior decoding, but also had comparable or better neural prediction than the alternatives such as PSID or RNNs that were trained unsupervised. And finally, of course, we have to compare to benchmarks. So we compared with LSTMs that were trained either to predict neural activity or behavior, and with a concurrently developed method called Zebra. And we found that both in our data sets as well as the original data set in the Zebra paper, that DPAT could outperform them both in terms of neural prediction as well as behavior decoding. All right, so I'm almost through half of my talk, and all I've talked about is the decoding block, right? So for some application, this is enough. For motor BCIs, you decode movement and you move a prosthetic, you're essentially mostly done, unless you want to write in sensory input. That's a separate question that Jennifer, for example, talked about yesterday. But in these BCIs that we think about for regulation of mental states or mood, this is not enough. So think about this. If I even know somebody's mood perfectly over time, that doesn't tell me how to stimulate their brain, how to give them therapy in order to regulate their mood states. So what we need additionally are input-output models that tell us the effect of therapy on brain activity and on the underlying mental state, essentially these input-output models. So that's the second major challenge that we have to address in these new types of BCIs. So what we need here is essentially a model of this box. How does simulation, for example, if you care about neuromodulation or electrical stimulation, how does that change brain activity and the underlying mood? Now, in order to solve this problem, we've developed data-driven input-output models that can describe this relationship. And the way we did this was by incorporating an input term into our state space or dynamical system model. So this is basically saying, oh, the input drives my low-dimensional representation, and through that neural activity. This is great. But the problem is, how do we fit this model, right? We need data to fit this model, and we need rich enough data. And collecting data in this case means that I have to stimulate the brain to get the input-output data. But how do I stimulate in order to get informative data sets? So the first step for us was to actually design stimulation patterns that excited brain activity sufficiently to get these data. And we developed a waveform we call binary noise electrical stimulation. So the idea here is that you start with a biphasic pulse. These are pulses that are typically used in the clinic. But instead of applying it with a fixed frequency and amplitude, we stochastically change the frequency and amplitude according to a coin flip. So with 50% probability, you keep it at one level. With 50%, you switch to another level. So we show that by doing this, we can get a waveform that's persistently exciting the brain and actually is critical in this input-output modeling. So we did this first in a simulation theoretical paper, and then we said, okay, we have to do it in the brain. So we asked Bijan, can you please apply this in your animal models? So we went ahead and applied our binary noise pattern in monkeys in the orbitofrontal cortex and other brain sites and recorded the response across a multi-regional brain networks, and then fitted our models. And what we found was that indeed we could predict how neural activity changes in response to this time-varying stimulation through these models, thus starting to address that second challenge that I mentioned. Another interesting observation here was that while we were stimulating one site in the brain, the response was actually distributed across a network of brain regions, but the strength of the response was variable, meaning one site was more strongly responding, one was less strongly responding, and so on. So then the question was, why is that? And our hypothesis was this is likely related to at-risk connectivity, functional connectivity, between the stimulation site and these different sites, meaning if I'm more connected to you even prior to stimulation, I probably respond more strongly when you stimulate. So we went ahead and tested this hypothesis by devising this connectivity measure called controllability that essentially tells you how much energy you need at a source node in order to change activity at different target nodes. And we found that indeed our hypothesis was validated. So when we look at controllability, the stronger the connectivity is to a site in data without any stimulation, the stronger that site actually responds during stimulation, just providing the scientific validation of our modeling framework as well. OK, so we have now an input-output model that describes the effect of stimulation on neural activity. But if you notice, I didn't talk at all about behavior. But if you're building a closed-loop system, at the end of the day, you don't want to modulate activity. You want to modulate behavioral outcomes. So what we really need is to describe the effect of input jointly on neural and behavioral data. This input could be neuromodulation. It could be pharmacological innervation, like drugs. It could be any kind of intervention. It could be sensory input. It could be another region's brain activity. So how do we do this? We essentially, to do this, extended our PSID framework, which is a joint neural behavioral model, by including the effect of input inside it. So this time, the goal of this input PSID or IPSID was to dissociate the behaviorally relevant neural patterns, not only from other patterns, but also from inputs that were coming into the brain. So by doing this, you're essentially getting to the intrinsic computation, intrinsic dynamics in the brain. And we call this input PSID or IPSID. Again, this is an analytical method, so there's a lot of detail. Intuitively, you put in the input, you come up with projections that not only find a shared subspace between neural activity and behavior, but also subtract the effects of input through oblique projections. But again, I'm not going to go into the mathematical details. So how does this work? What can we do with this? To validate this and see how well we get the intrinsic dynamics, what we can look at is the eigenvalues of this matrix A, which is called the state transition matrix. So essentially it tells you how the state moves from time t to t+1. So it's essentially telling you the dynamics. The eigenvalues here, what they tell you is what is the frequency with which your neural activity oscillates over time in response to excitation, and the time decay with which your neural dynamics decay over time in response to excitation. So we went ahead and fitted these models and looked at these eigenmodes or eigenvalues in our neural data. So this was the data set we looked at. This is, again, a public data set. And there is input here explicitly in the form of sensory input. So this monkey is instructed to go specific targets on this grid. So you can think of the target location as input to the brain. Hey, go here, go there. This is a sensory input. And then you have neural recordings, and you have the cursor movements, behavioral movement trajectories. So we said, OK, let's fit IPSID, and let's fit an unsupervised method and compare them. So we found very different eigenmodes, first of all. And IPSID could actually, again, decode behavior more accurately, implying that we get more accurate intrinsic behaviorally relevant dynamics using IPSID. While this is great, that's not the main capability, though, that IPSID provides. Because IPSID can take into account differences in inputs, what it can allow you to do is to look at differences in intrinsic dynamics and computations across different tasks that have different inputs without confounding your results by those differences, because you can take them into account. So we said, OK, let's now look at another completely independent data set, in this case from the Miller lab, with a monkey using a manipulandum to reach around. So we had 3 data sets from 3 animals, and we had 2 distinct tasks. First, we used the unsupervised method that took into account input to look at overall intrinsic neural dynamics across monkeys and tasks. And what you find is they're very different, right? You can see, just look at the colors and the locations. They're very different. This kind of makes sense. I mean, these are different animals. They're doing different things. They have different mental and cognitive states. Then we said, OK, what if I just zoom in on the behaviorally relevant or task-relevant components of my neural dynamics, which I can get with IPSID? What do I find? And this is what we found. So you can see that they're remarkably similar across monkeys and tasks, unlike the overall intrinsic dynamics. So there are these preserved neural dynamics and computation across distinct tasks and animals that we can extract with this new method. Now, IPSID was an extension of PSID, so linear, obviously. Why don't we go nonlinear? So we just this year We had a paper that developed nonlinear RNNs that can do this disentanglement of input-driven and intrinsic dynamics, called this method BRAID. Again, it has two models that allows us to do this disentanglement, a predictive model that basically predicts the immediate effect of input, and then a generative model that feed-forward predicts the neural data from there to get you the intrinsic dynamics. So we developed this, and we said, OK, let's see if we can get better intrinsic dynamics with this nonlinear method. So again, on these data sets that I've shown you, we looked at this method BRAID versus the linear version. You can think of it as IPSID, and also alternative models, and you can see that it does indeed better. So for even capturing intrinsic dynamics, these nonlinearities are important. OK. So this is how we're thinking about incorporating the effect of input. And as I mentioned, that's a critical step in building these BCIs. But now what we have to do is to combine the decoder with the input-output model to actually deliver therapy, to actually optimize therapy in closed loop and in real time. And that's the idea of developing this control strategy or this closed loop control algorithm. And that's the step that we haven't done yet, and we are working on right now because it's a very challenging step. But I want to give you a little bit of intuition of how these two fit together to give you a controller. So let's say you have an input-output model. What this does, it tells you how changing the simulation changes neural activity, right? Now let's say you have a decoder, let's say a mood decoder. What this does is tells you how that neural activity is representing mood. So if we combine these two models, we're describing the effect of stimulation on mood or on any behavioral indication through neural activity. And that is what allows us to optimize stimulation in order to regulate it. Of course, this is just an intuition. There's a lot of development we have to do to build these, so those are what we're working on right now. What are some of the other directions that we are interested in and are the kind of, I feel like, the future of building these BCI systems? So the first one is to go towards multimodal neurotechnologies. In particular, if you think about everything I've talked about right now, in each case, I was using a single modality. Sometimes it was spikes, sometimes it was ECOG, sometimes it was LFP, but never was it all of them or a couple of them simultaneously. So what we envision is to build these kind of multimodal neurotechnologies that can use simultaneously multiple modalities of electrophysiology that you may be recording at the same time, such as spikes and LFP. But then can go beyond that, also incorporate neuroimaging modalities, optical, magnetic, acoustic, or even physiological or wearable data. Think about heart rate variability, skin conductance. They are also telling you something about the mental and brain states. So can we fuse all of these modalities to get the best readout? We also care about different modalities of input. I talked about electrical stimulation. But what about magnetic stimulation? That's non-invasive. What about optogenetic stimulation? What about focused ultrasound? Again, non-invasive modality. Or even pharmacological intervention. Can we develop closed-loop drug delivery systems using these BCI technologies? Now, we've taken some steps already towards these multimodal technologies. In particular, we've allowed our models to go multi-scale with different scales of electrophysiology. I'm showing you different electrotypes that you can have in the brain. I talked about the ECOG grids that you can see. That was what we used to decode mood. I talked about LFPs and spikes from intracortical electrodes. That's what I showed you with movement decoding. So if you have multiple of them simultaneously, can we essentially do sensor fusion for the brain and go multi-scale? So we showed in a relatively recent paper that indeed with spiking and LFP, we can do this. So we were interested in looking at representation of naturalistic movement in spikes and LFP and their relationship. So basically, we took our favorite data set again. We extracted LFPs and spikes from it. And then we developed an encoding model that this time was multi-scale, meaning it simultaneously told us how the brain state is represented in LFPs and in spikes. And once we developed this, we also developed a decoder that then fused these two modalities and asked, OK, can we do better? And indeed, we could. So I'm showing you, for example, decoding of shoulder elevation with spikes alone. And this is how we can do jointly with LFP and spike. You can see we can do much better. There's also benefit in terms of robustness because LFPs last much longer than spikes, for example, in a chronic BCI setting. So this is different modalities of electrophysiology that we can fuse. We just recently also extended our neurobehavioral models to imaging modalities. So for example, wide field calcium imaging or focused ultrasound. The imaging modalities, of course, have distinct challenges in this case because you have very complex correlations, both locally and globally in an image that you have to capture. And a lot of these have no relevance to behavior. So we developed, again, deep learning methods that captured local relationships using convolutions, and then global relationship using self-attention mechanisms in recurrences to predict behavior and neural activity. Of course, you don't need to follow that. There's a lot of details I'm avoiding, but that's kind of the intuition. And what we found was that if you look at the method S-spine, you can see like you are capturing relations between more global regions, right? Like more globally across the brain in that wide field image, versus if you have no attentional mechanism that you cannot get more global relationships. And this was reflected in better decoding, both compared to ablations of S-spine as well as with alternatives such as Zebra and DPAP. And these are just examples. Of course, our vision is to go towards this full-blown kind of multimodal model. Now, another direction that we're very, very excited about for the future of neurotech and BCIs is to go towards foundation models of brain activity. So what is a foundation model and why should we care? If you think about the models I've shown you so far, each model was trained on an individual's data separately, right? So you get some data, you train your model, you decode it. Yes, of course you do cross-validation. Of course you do on different days, but it's from the same subject. But if you have more and more subjects implanted, or you have EEG or non-invasive modalities from more and more subjects, can you utilize all of those data to get one foundational models that actually generalizes across subjects? So the idea here that you take all of your data sets, you pre-train one unified foundational model, and this model is rich enough that can represent the representation, essentially can contain the representation across different individuals. So if a new subject comes in, all you have to do is simply to fine-tune that learned model that has used a lot of data that you already have, a little bit of data, and you get a great model for the new subject. So that generalizability across subject, that ability to use a lot of data, is one reason to go towards foundation models. The other reason to do this is because you can generalize across different behavioral modalities and contexts. Whether you're decoding movements, or decoding gaze, or decoding pain, or decoding any state you want, if you have a rich representation, you have captured all of those semantic meanings. Of course, we have to develop these foundation models, and that's the step, again, we are currently intending to take on. So the idea here is you take the neural activity from different subjects, you first tokenize it by encoding time structure, temporal structure, a spatial structure, which brain regions they're coming from, and then you plug it into a transformer backbone to get embeddings that have semantic information, and then you use that for different types of brain state classification. So I think that's a very promising step as well towards these generalizable neurotechnologies. And because these neurotechnologies will be multimodal and generalizable, we hope that they can seamlessly extend across a variety of hardware devices that are being developed today across a lot of beautiful work from many companies. I've shown some of them here. This is not exhaustive by any means, but these are some of the companies that you've also heard about from yesterday. And we hope that they can also extend across a variety of brain conditions, whether you're talking about mood disorders, or chronic pain, or obsessive compulsive disorder, or movement disorder, ALS, or paralysis. So at the end of the day, our vision is to develop an AI-based system, a closed-loop AI-based system that can, of course, extract mental and behavioral states from human brain networks, but can actually go beyond that and thinking about regulating these states as well as reading them out towards potentially revolutionizing invasive or non-invasive therapies for millions of patients that suffer from neurological and mental disorders. So with that, I would like to thank my lab members who have done all of the work I've shown you here, as well as the funding sources, and thank the organizers again for getting us together in this beautiful venue to discuss science. Thank you, and I'll take any questions.
Thank you for a great talk. It was great to see it in person rather than just read the papers. One thing that you didn't hit on is the ability of the models to tell us about the mechanisms. So because of the problems of different individuals having different types of electrodes in different places, and because you have limited focal resolution of your stimulation, what do you think about the future for getting into the mechanisms? Is it only going to be the foundational model that will finally tell us more about the mechanisms, or do you see another way to get there?
Because of, you think, the variability across
patients.
Yeah. So I mean, yes. So in epilepsy patients in particular, where I prototype a lot of the technologies I developed, there's a lot of variability. But there are some consistencies that you can tap into. For example, you always get some limbic regions, amygdala, hippocampus there, or orbitofrontal cortex that you can look at. But indeed, if your recordings across individuals are very variable, and if you're missing some brain nodes, the way to fill it in is to use many individuals. And that way, if you record my amygdala and hippocampus, but not my orbitofrontal cortex, and you have orbitofrontal cortex from somebody else, by putting it into a foundation model, you can get a more complete map of the brain regions and the effect of, for example, stimulation on a more complete functional network. So that could be one way to go around it through foundation modeling. Of course, foundation models, though, are very, they're transformers, so they're not as interpretable as the linear dynamical system models. So there's trade-offs, and I think we can use a combination of strategies, foundation modeling when we want a more complete map, and linear dynamical system modeling to get more to the dynamics, right? How the dynamics evolve over time. And their intermediate model, like Define that I talked about, that has a nonlinear embedding, but linear dynamics is an intermediate model. So I think we need a multi-pronged approach to getting interpretability and mechanism. Yes.
Hello. I was curious about the brain signals that you're using for decoding. So in the subfield of this that I'm familiar with that decodes speech, it seems like high gamma is the signal that everyone loves because of the correspondence with population spiking. Are you just using like the raw LFP, or are you also looking at high gamma or other signals like that?
Yeah, that's a fantastic question. So we do both. So actually, we did study the difference between decoding from raw LFP and LFP powers like gamma, beta, alpha in the context of movements, not speech, but movements, arm movements. And what I showed you was that if we use nonlinear DPAD modeling, for example, on raw LFP, we can do better than decoding from the power band features. And this makes sense because power band features is a predefined computation. So it's a pre-processing you do on raw LFP. So theoretically, you should at least be able to do as well as the power band features with the right model that gives you the capacity to discover those power band features. So what we found is that if you have a model that has enough capacity like DPAD, you can actually do better with raw LFPs because powers discard some information. But of course, if you are using more simple models like linear models, you probably can benefit from doing your power computations because those are nonlinear computations. So I think in general, it's good to move towards modeling raw signals with models with more capacity, but in some cases, it makes sense still to use power features.
Thanks.
Hi. Amazing talk. Thank you so much. Yeah. It reminds me that years ago, so I'm doing FNIRS and mostly signal processing. And then years ago when deep learning came out, and I was like, oh, that's cool. I can use deep learning to process my data. And then looking at the applications at the time, computer vision or language models, their training data set is massive. And then when we come to neuroscience, neuroimaging, and then we have limited sample size. And then even though there are some methods that you don't need massive data sets to train your model, but when it comes to neuroimaging data sets, it's like uncomparable. It's like too small, even though we combine so many data sets together.
Yeah.
And I don't know if it applies to BCI or not, or what do you think about this data sample size problem?
Yeah, no, that's a fantastic question. And indeed, that's why I cannot plug my brain data into ChatGPT, right? Because I just cannot pre-train it. I don't have enough data. Yeah. So I think brain data brings in unique challenges. That's why we can't take off-the-shelf method. That's why my lab exists, because we innovate on the AI front, right? So we think about, okay, how do we build models that are not super over-parameterized, that we can actually train with the limited data sets that we have? Yeah. How do we take into account behavioral data? So if I can't fit the entire representation, can I fit the behaviorally relevant representation better by not just looking unsupervised on neural activity, but also looking supervised with behavior? So there are different approaches one can get to get more efficient models for neurotechnologies that do not require super large data sets. We obviously don't have. The other challenge for us is heterogeneity, right? From one subject to the other, and we just talked about it a little bit. Yeah. Our data sets are very heterogeneous. Language is not like that. Yeah. So we definitely need innovation on the AI front, both on the model architecture, learning algorithms, and inference to do this for the brain and to do this for neurotech, where we also have the constraint of real-time computations.
Okay. Yeah, thank you.
No problem.
So we have a question from the Zoom. So Dr. Shanechi, your work on decoding affective states from neural signals and implementing closed-loop stimulation offers a powerful paradigm for interfacing with the brain in real time. From your perspective, could such systems be extended beyond clinical therapy towards shaping adaptive environments, such as architectural or urban, that respond dynamically to collective neural emotional states? And if so, how might we reconcile the individual specificity of brain signals with the design of shared public spaces meant to foster well-being?
Yeah, that's a great question. So as I mentioned, so the neuromodulation application is just one. From a formulation perspective, you don't have to have the input to be a therapy, right? It could be a sensory stimulation, a sensory stimuli that you present your subject. So the question is, in any application, if you can get the cognitive and affective states that are relevant to your application at hand, then you can use that information to guide your user. For example, we had a project in which we were recording actually EEG non-invasively to enhance decision-making. We decoded confidence in decision and used that confidence to decide whether the subject needs more information to make a more informed or better decision in their everyday life. So the question is, what are the relevant brain states to a particular application? Can we decode them and then use that information to optimize the input, which could be sensory input, information that you provide them, or a mode of therapy? So absolutely, these architectures in the non-invasive form can be extended to a lot of everyday applications beyond therapy.
Well, I first want to say my name is Lava, and thank you so much for your incredible talk you just did.
Yeah.
I mean, you guys are working on insanely cutting-edge stuff here. But to my question, I recently connected with an individual, and they were talking about how they're currently working on creating an AI system that can communicate between different autonomous vehicles. But I was thinking how that could be useful for you guys, because you guys want to create a multimodal system. And that will involve trying to connect different technologies that use different hardwares. And that's exactly what they're doing. Like, how do you think that would be useful for what you guys are doing right now?
Yeah, so when you think about multiple modalities, I mean, I don't know the specifics of what they're doing, but one question would be, are there shared information between the modalities? You can think of that shared information as a communication channel, if you will. So some of the techniques we develop are all about finding shared structure across completely distinct signal sources. Like behavior and neural activity is one example. One brain region and the other brain region is another example. So some of these techniques that kind of communicate essentially shared information can be utilized to find shared information between, say, behavior and neural activity towards better decoding, communication across individuals, right? So if I and you are involved in a conversation or a social interaction, there's going to be shared information in our brains. Can we actually extract those shared information patterns towards social interactions and so on? So there are, I'm not doing any of this, but you can envision these techniques will be utilized in the future, obviously in the non-invasive domain.
Thank you so much.
No problem.
So we have another question. This one from Catherine Mickelson. Hi, thank you for an incredibly exciting talk. Thinking about moving toward non-invasive technologies, how important are the faster frequencies of the LFP for your decoder if we're thinking about using a non-invasive method like NIRS, which relies on the much slower bolt signal?
Yeah, fantastic question. So as a control analysis in one of our papers, we actually looked at low-frequency components of LFP alone. And we found that we could do as well of a decoding with those low-frequency components. So we did not need gamma, actually. Again, once you put in a descriptive enough model that can extract these nonlinear patterns in data, the decoding, even using low-frequency bands of LFP, for the behaviors we were looking at, were comparable to high-frequency bands, and maybe a little bit worse than spikes. So there's definitely potential in using signals that have low frequency components to do BCI decoding. Yes.
Hi, thank you for a wonderful talk. I was curious about, can you provide more insight or comment on the regulation in terms of mood? Because I think you mentioned the mood data is rather sparse compared to the behavior. Movement, we can measure a lot of things like positioning in the hand, but it's kind of hard to measure move accurately, and it's somehow a little bit subjective experience. I was curious about, in terms of this kind of setting, do you think there's an approach that we can maybe not just attack this disability, but also maybe flourishing? How do we improve people human experience?
Yeah, no, absolutely. That's a critical question. So, as he's mentioning, right, mood, how do we measure it? Forget neural activity, forget BCIs. We just want to measure somebody's mood over time to help them, just behaviorally. I mean, with movements, you see my arm movement. You can measure it very accurately and objectively. That is not the case with something like mood. Right now, our best surrogate is just asking people with questionnaires, how do you feel? This is subjective, it's sparse, it's very noisy. So can we, forgetting about even the brain, get better behavioral measures of mood? And indeed, we are working on that, as well as getting better physiological measures of mood. So one thing one can do is to look at facial expressions. You can look at speech pattern. These days, with large language model, language carries a lot of information also about how somebody is feeling. So we are looking at different behavioral modalities that can track somebody's symptom state or mood over time that can give us a behavioral feedback signal, even if we don't have neural recordings in the form of language, audio-visual modalities. The other way to track some of these mental states is physiological modalities. So if you think about heart rate variability, cortisol levels, all of those are indicative of some mental states. So we are actually developing systems that can get wearable data and use that to also decode these mental states. So we're taking a multimodal behavioral, physiological, neural approach to getting these affective and mood states. When we have brain activity, great. If we don't have it, we can build these multimodal systems with behavioral data or physiological data.
Just a follow-up. So do you think the bottleneck right now is the a decoding of the mood, or other part of the whole closed loop pipeline?
So we've shown we can do the decoding. So if you want to say it's no longer the bottleneck it used to be, but we need a lot of improvement even for that, because the explained variance is what, 40%, something like that, the best you can do. that's not satisfying, right? So there's a lot of work done on the decoding because of these machine learning challenges. And some of it, I think, foundation models can solve. That's why we are pursuing some. We want to pursue some of those. The other challenge is the controller. I think that's a huge challenge. So let's say you have an AI algorithm that can decode mood. You still have to figure out how do I adjust their therapy? How do I adjust their stimulation? How do I adjust their drug? How do I ask them when to go see their doctor, right? So that control algorithm, the decision-making algorithm that combines with the decoder is a huge challenge. And I think then one next frontier for the field would be closed-loop control combined with decoding, not just decoding.
Thank you so much.
Yeah, no problem.
Hello, thank you very much for this talk. My name is Alex Cerullo. I'm from the University of Rhode Island, and I've been working mainly with EEG FNIR systems up till now. And one of the large hurdles that we need to struggle with is the fact that on a day-to-day level, the brain states change massively, even on the same subject. And so in the case of multiple subjects over a long period of time, when we're inducing a control system that then remodulates the brain constantly, do you see a concern where applying some sort of electrical stimulation or pharmaceutical drugs over time will change the neural correlates in ways that you weren't expecting or that the decoder can't really account for?
Yeah, absolutely. So when you have inputs, it's going to change the brain. We know there's plasticity, we know there's habituation, and there's adaptation in the brain. But we can tackle those. So we can develop adaptive models and adaptive algorithms that you can either, for example, intermittently refit so that you can adjust to the new variations in the encoding and in the representation. Or even in the linear case, we've developed continuously adaptive models that can essentially say, hey, how's your representation changing over time? Let me capture that. And the way you do that is your model makes a prediction. You look at what the actual signal is. If they're very different, then your model is no longer any good. So you want to adjust it based on that error that you see. So we've been thinking about developing adaptive and calibration algorithms that can address exactly those problems that you mentioned.
I'm viewing this through the lens of, say, somebody with ADHD taking medication, and over time a tolerance is built up, yes. And even the therapists and the psychologists don't entirely understand how that brain reacts to it. We need to devise a system that would be able to account for the medication and then
you have to see how the dose response changed, right? So the dose response model is essentially that input-output model that I mentioned. I talked about neural activity, but this could be just an input-output model on symptom states or behavioral outcomes, or I don't know, you can measure behavioral outcomes in many different ways. So the question is, can we build adaptive models that tell us how the dose response is changing over time so we can adjust it optimally?
Thank you very much.
No problem.
Hi, thank you so much for the wonderful and exciting talk. My question is, if something can be regulated, it can also be manipulated. So I was wondering if there were very important ethical considerations that you had when developing and using these models.
Yeah, absolutely. Ethics is huge in what we do, and I would say even decoding. I mean, things can be like privacy, right? Like if somebody can get access to your brain signals, there's huge ethical challenges there too. It's not just about regulation, but yes, indeed, ethical considerations are critical. So in all of our grants, we have neuroethicists who work. I'm by no means an expert in this. I cannot comment, but we have neuroethicists that look at this from multiple lenses, from the lens of privacy, agency, self-trust. Like if the decoder says, this is my mood, but I don't feel that way. So these are all ethical challenges that our neuroethicists specifically study in a systematic manner, and I think the science and the ethics should go hand in hand for sure.
Thank you.
Yeah, no problem.
There are so many other questions, but our time is over. Thank you for
Thank you.
your fantastic presentation.
Thank you.
Thanks everyone for your attention.
Thank you very much.